Okay. Uh, that's about it. And I guess now the CVN folks are joining us. CVN folks. Now this is only for people who are registered through CVN and are not available on campus. So I don't care if you're skipping class and watching the tapes on CVN, that's fine with me. But you still, if you're a student registered at Columbia and not only through CVN, get your homework in on time. Here, this does not apply to you. But the students taking it on CVN who actually work at companies and such or live in China, you have a 48-hour extension in general on the homework. Okay? Any questions? So the plan of action for today, no questions. I'll tell you, I'm actually a student this term. Faculty and officers are allowed to take a class, so I'm taking a class in Spanish. So I can sympathize with all of you. Sitting there, like the fear of failure and all that kind of thing. I feel it too, and the professor telling me, you got to get here on time. So I make an effort to get there on time. And it's not 9 in the morning. It's 6 at night or 7 at night or something. Anyhow, so I am a student this term too. And I don't know how well I'm going to do. So, That's right. My wife is Colombian. In fact, the reason I'm taking Spanish is because we're having a baby, and she wants us to speak Spanish. So I have 6 months to learn. I already speak some, but there's a lot of room for improvement. Okay. Well, all right. Before we get started, since I brought up this thing about Layton, I'll tell you the story about Tom Layton. So I was an undergrad at MIT, and you know how they have this URIP program here, URIP. Well, at MIT they had this UROP program, and he happened to be my supervisor, and they paid $7 or $8 an hour, which was like a lot more money you could make anywhere else. So I was just doing the job for the money. So I wrote some simulation code for him and a grad student. And after doing that for like 3 weeks, he's like, "Great, now we'll run the simulations and we'll write a paper." And I was like, "I don't want to run simulations, I like writing code. That part sounded boring, so I just quit." And I want to see tomorrow if Tom remembers me. So I guess it wasn't that good of a story. Anyway, he also founded a company, Akamai, and became a multi-billionaire, and took a lot of undergrad students that worked with him to the company. So I could have been possibly been a multi-millionaire. Sleeping late every day. Okay. People find that amusing, right? It's like all right, you blew it with this, MIT prof, this brilliant guy. Who cares? But billionaire, that's important. Then I really blew it, right? Okay. Any questions? No. Oh yeah. Yeah, you can get it to me early. Early is always fine. Under my door, in my mailbox, and mailboxes are currently moved. So before class, I'll run up and check my mailbox. So you got to get into my mailbox by about 8:55, something like that. 9 o'clock. 9 o'clock is the deadline. Okay, get in my mailbox by 9. Yeah. So if you have trouble waking up early, just instead of thinking you have 7 days to do the homework, you got 6.5. Okay. All right. Today, Wednesday, and we're gonna do a quick run through of discrete probability, which I'm assuming everybody's seen before. So I'm gonna run through it and really just hit on some key points, because there's some ideas we're gonna use over and over again, and I mean over and over again a lot. And then next week we'll do continuous probability. Okay. Any questions or concerns about that? All right, so feel free to ask questions. Stop me now. The way I use probability for this course, again, there are just a few concepts that we use over and over and over again. I get really annoyed when students come to my office hours at the end of the term and still haven't grasped the 4 or 5 concepts that we got. So please, please, please try and remember them. There's not that many. Okay? That's coming from up here, right? Oh. Okay. What we mean by discrete will become clearer when we start talking about continuous probability. So probability is a very confusing subject for a lot of people, including myself. I had trouble with it initially, and sometimes you still always get confused a little bit. It's the science of predicting, the science of prediction, I guess. Right? What are the odds? Right? You ever watch? I'm blanking on the name. Poker. The poker tournaments they have on ESPN, right? Where they put out the guy's cards and they say, oh, so and so's got a 52% chance of winning. Right? That's probability. They're using probability to figure out those odds, right? All right. So all right. So we have to get a little bit abstract. So there's this thing called omega, which is the sample space. So you've got some event, okay? Like the simplest one is rolling, flipping a coin is the simplest one. So let's say you're flipping a coin. Let's just flip it 10 times. Okay? Then your sample space, am I using the right term here? Event space. Let's go with event space. Yeah, and one other thing about the way I lecture is I make a lot of mistakes. I change my mind a lot. So catching out notes a lot. So usually, like I'll say something and then change my mind about half a minute later. So just be prepared for that. So there's an example. Sample to event space. Okay, and in the event space, we have all possible outcomes of our events. That's going to happen in the future. So for instance, you flip a coin 10 times, you can have heads, heads, heads. So again, let's change it to 3 times, just to make life easier for me. It could be heads, 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 tails, heads, tails, heads, heads, tails, tails. Where am I? Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. And that's our whole space right there. So get rid of that. So with me so far? That's the event space there. And of course, you can have weird event spaces. We're not going to worry about them so much in this course. Like flip a coin an infinite number of times. Here's an example. Okay, and then obviously there are so many possible outcomes. In mathematics, there's an uncountable number of possible outcomes. Okay, anybody here familiar with this notion of uncountable? for this course, it certainly doesn't matter. But basically, I can't even hope to enumerate all possible outcomes, right? So there's heads, 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 heads every time, you know, until, you know, forever. And then you could have heads, tails, right? And the point is there's just an infinite, I mean, in this case, even uncountable, I don't know, number of possible outcomes. Okay? That's the event space. Okay, so don't worry about the weird ones right now. Each event has a certain likelihood. Each outcome has a certain likelihood of each possible outcome. Each possible outcome has a certain likelihood of happening. The value assigned to likelihood is called its probability. Okay, so this space omega is made up of some little omegas. Maybe there's a finite number of them, maybe not. Okay, where little omega sub I is a possible outcome. Okay, so for instance, in our example above, it could be heads, tails, heads. We call that W4. Okay? And each outcome has a probability of happening. So the probability of W sub I, we could say, is 0.125. Okay? And there are some basic rules in probability, one of them being that only one outcome occurs. Right? So they are mutually exclusive. And the sum of their probabilities. So the sum over all omega sub I in omega, the sum of the omega sub i's is going to equal 1. Okay? Everybody got it? Omega, the space of all possible. You're running some experiments, so it's the set of all possible outcomes of that experiment. Each possible outcome has some probability of occurring. So I should also add 0 is less than or equal to p of w sub I is less than or equal to 1 in general. 0 means the event can't possibly happen. 1 means the event's always going to happen. Okay, and some event's going to happen. 1 means it happens. So the sum over all events equals 1 means that event's going to happen. Okay? Everyone with me so far? Okay. And something that's very useful in probability is something called the random variable, which I think this is the point where people really start to get confused, although they generally don't know it. But usually when you sort of lost control of your understanding, the problem is with the understanding of a random variable. So what is a random variable? A random variable is just a function. It's rarely taught that way, and people rarely think of it that way. Okay? But if f is a random variable, then f of omega is some value. Okay, so for instance, I could define the function f, the random variable f, is the number of heads in the, what did I call it? Possible outcome to which it is being applied. Okay, so f of HHH would be 3, f of HTH would be 2, f of TTT would be 0, right? Just a function, applying it to these omega sub i's, okay? And then sometimes there's a shortcut. We might say, let f be the number of heads that appear in three coin tosses. Right, this is how you probably see it a lot of the time in a probability class. But really, what should be going through your head is, I'm tossing the coin 3 times. Okay, the set of all possible outcomes is the different way in which the 3 coin tosses can turn up, and I'm going to apply this function f to it. That's just going to count the number of times that heads appears. Okay? So let me just make one additional comment. So comment, even if the event space is weird, sometimes you can still have, let's say, normal random variable definitions. So what do I mean by that? So for instance, again, consider flipping a coin an infinite number of times. Okay. The problem here is that the probability of any possible outcome, when you're talking about flipping a coin an infinite number of times, the probability of that outcome is always going to be 0. And what's the problem? You get heads an infinite number of times. I mean, it's not going to happen. You take any infinite sequence, it's going to have probability 0. Yet you sum them up together, it still has to add up to 1. I mean, that's why I'm saying it's weird. I mean, this is something. There's a whole advanced topic in mathematics called measure theory that deals with these weirdnesses that we don't really deal with day to day. Okay, but so even though you have this property where you can't measure the probability of an individual event, you can still have random variables like let f equal the number of heads in first 5 coin tosses, first 5 tosses. Okay, that's still easy to measure, right? I have an infinite sequence of tosses, but I don't care. I just look at the first 5. I count the number of heads there. I can still measure that, right? Or let f equal 7 if the 9th and 10th tosses match, and 2 otherwise. I can really define random variables any way I want. People with me? Okay, and there's one very important specific kind of random variable we're going to consider. and you'll see it's going to be extremely useful, especially when we do computations of expectations. So it's called the indicator random variable. Okay, so written I of omega equals 1 if something holds, 0 otherwise. Okay, that's an indicator. It only equals 0 or 1, and 1 means the thing we're interested in happened. The event we're looking at, it happened. 0 means it didn't happen. Okay, so for instance, let I of omega be 1 if the first and third coin flips are the same, 0 otherwise. That's an indicator for first and third flips being the same. Okay? Questions? Comments? Critique? So for those of you who weren't here last time, I don't know why it happens. My writing always tends to start slanting downward. Always. Almost always. Probability 0.8. All right? Okay. Okay. Again, for those of you who got here late, any information you want, homeworks that you didn't pick up, that's new homework, not your own homework. It's all available. It'll always once it's made available in class, it'll also be available on the website. So, in fact, homework number 1 is supposed to be handed out today. I don't know if my assistant's going to get it done in time. If not, it's available on the website as we speak, and I'll have it handed out next Wednesday. But if you want to get started on it right away, it's on the website. Okay, now here's the thing. Events, possible outcomes, that's the omegas, are mutually exclusive. Okay? I said that already. You don't have to write it down again. But you can. So whenever we talk about events happening, either one event happens or the other event happens. But how do I say this? Yeah. This need not be the case for a random variable. I'm jumping the gun here. Well, let me say it anyhow. What I forgot to mention was, right? You can talk about the probability of an event happening. An event has a probability, but you can also talk about what's the probability that a random variable applied to the event that actually happened has a certain value. Okay? So for instance, this is, what's the probability that that of our 3 coin tosses, HTH was the outcome. And here we're saying something like what's the probability that of the 3 coin tosses, heads came up twice. Okay? Or, i.e., the outcome was heads came up twice. HTH, HHT, THH. Okay? All right. Let me just do it like that for now. You can also ask things like, what's the probability that f of w is greater than x? What's the probability that f of w is less than x, less than or equal to x, greater than or equal to x, between y and x? And there's all sorts of questions you can ask like that. And what are we saying when we ask this question? What we're saying is, well, the probability that let's just take the easy one. Probability that f of w equals x, or what this is the sum over the set of omega where f of omega equals x, probability of omega. Okay, I'm taking all the omegas that satisfy this condition, and I'm summing their probabilities together. Again, not worrying about the weird probability spaces, event spaces. People follow this? Or you want to see an example? Who wants to see an example? All right. So I do this. We're going to flip a fair coin. Three times. Okay, fair meaning comes up heads with probability 0.5, comes up tails with probability 0.5. Okay, and let f of omega be the number of heads actually let's you know what, forget this fairness business. Let's just say we flip a coin 3 times, and let f of w be the number of heads. Okay, and let's just say, in fact, let's not make it a fair coin. Let's make it be an unfair coin. So certain outcomes are more likely than others. So let's look at the 8 possible outcomes. For those of you who took 3910 with me, right, it comes in handy here. Right, instead of zeros and ones, it's H's and T's. Just writing them down, you know, in the right order, so you get them all. Okay, And because it's an unfair coin, I can assign whatever probabilities I feel like to these different events, as long as they add up to 1. So let's say heads, 3 heads never comes up. This comes up 0.1, 0.1, 0.15, 0.15, 0.2. So that's 10, 20, 50, 70, 0.29, 0.01. Okay, should add up to 1, right? So if you do this experiment 100 billion times, this should come up 10% of the time, 10% of the time, 15% of the time, 15% of the time, 1% of the time, 20% of the time, 29% of the time. That should be the outcome. If you were to flip this coin 3 times, over and over and over and over again, like 1 billion times. Okay? So now I can ask, what's the probability that f of w, let's do equals 2. Heads comes out twice. Okay? So that's this one, this one, this one, and that's it. Right? So what I'm saying is the probability that heads comes out twice is p of ht plus p of hth plus p of thh, which for this weird coin is 0.1 plus 0.1 plus 0.15, which is 0.35. Okay? So with this weird coin, the probability that you get 2 heads exactly is 0.35. Because there are 3 events for which you get 2 heads, and this one will come up 10% of the time, this one will come up 10% of the time, this one will come up 15% of the time, hence 35% of the time you can expect to get 2 heads. Right? Everyone with me? Okay. Somebody's using this computer. That's what was dinging before, but there's this little mouse running around on the screen. You can't see it though, right? No. Okay. Then I mean, they're not showing that on TV. There'd be no reason. Okay. Yeah. So now going back to that comment I made, where the possible outcomes are mutually exclusive, but this may not be the case for random variables. So what do I mean by that? So you can have more than one random variable. Describing the outcome. So for instance, f of omega is, as we've said before, the number of heads. And I could have g of omega be an indicator, which will be 1 if the second and third flip are the same and 0 otherwise. And let's again go with omega as the set of 3 coin tosses with the biased coin. Used previously. Okay? And now we can ask questions like, what's the probability that f of omega equals 2 and, that we'll use for and, or, well, let's just start using a comma, because that's what we're going to use for the rest of the course anyway. F of omega equals 2 and g of omega equals 1. Written in shorthand, is this probability f equals 2, g equals 1, where f and g are the random variables as described over there. Okay? So in our example, only one of those, right? These three satisfy f of omega equals 2, but only this last one satisfies g of omega equals 1, right? This is the only one where I said second and third tosses? Yeah. Only this one satisfies the second and third tosses are the same, okay? Also, this one satisfies second and third tosses are the same. This one satisfies that. This one satisfies that, but only this one satisfies both conditions, right? So this is just going to be for our example. This is going to be the probability that you have this toss, which for this weird coin that we're using is 0.15. Right? Everyone with me here? Okay. Well, you could also ask or. So that's and. You could also ask, what's the probability that f of omega equals 2, or, which I'll write like this. There's never a good symbol to use. G of omega equals 1. Okay. In this case, so it's either you get exactly 2 tosses that are heads, or the second and third tosses are the same. Okay, so that's the probability of HHH. Sorry, the second and third tosses are the same explicitly. So the second and third are the same for that. HHT, right? That's 2 heads. HTH, that's 2 heads. HTT, second and third are the same. THH, second and third are the same, and also 2 heads. THT, right, that doesn't satisfy either property. TTH, that doesn't satisfy either property, and TTT. Right? So you can add them up with the numbers over there. Figure out what the probability of head tosses or second and third toss are the same. F equals 2 or G equals 1. Now there's a notion of independence of 2 random variables, x and y. And the definition of independence, this is what it means. When someone says random variables are independent, it means, forget about intuition for a minute. This is explicitly what it means. That the probability that x equals something and that y equals something is just the probability that x equals that something times the probability that y equals that something for all x and y. That's little x and little y. For all possible values. So just to distinguish the big y's and big x's from the little ones. Put these little hats on there for a second. Okay? That's the definition. Somebody says to you, these 2 random variables are independent, that's what you think. Probability of x and y is probability of x times probability of y. Okay? Fortunately or unfortunately, because there's times when it's useful and there's times when it screws people up, there's also an intuition behind it. And independence is the right word for that intuition. Basically means knowing something about X tells you nothing about Y. Okay? So let's do some let's see. Well, why don't we ask? The F and G we considered before. Are F and G independent? Okay, suppose you wanted to answer this question. What do you do? Okay, most people would start thinking like, well, gee, if I know the number of heads, does that tell me anything about whether or not the second and third flip are the same? So that's the hard way to do it. The easy way is to go by the definition. To show that they're independent, we have to show for all values of x and y, this equals that. Or to show that they're not independent, we just have to come up with one instance where this doesn't equal that. Okay? So let's see. All right, let's try this one. Let's look at the probability that f equals 0. So we got no heads. Okay? And g equals 1. Okay? The probability that this happens, that we get no heads, that's just, we get all tails. Right? And g equals 1, when we get all tails, this happens to be true. Right? So the probability of this is 0.01. Everybody with me? Everybody with me? Okay. Does that equal the probability that f equals 0 times the probability that g equals 1? Well, this is also 0.01, right? And what's the probability that g equals 1? It's let me put a little notation over here. It's that case, it's this case, it's this case, and it's this case, right? Where the last two are the same. So 0, 0.15, 0.15, 0.01. So 0.31. Right, which equals 0.0031. Right? They're not equal. Hence, f and g are not independent. By definition. Okay? And if you want to use your intuition, well, suppose I tell you something about f. Okay? Suppose I tell you there are no heads. Well, intuitively, it rules out a bunch of cases, right? Well, I'm sorry. If I tell you there are no heads, you know it's all tails. You know that the last two flips got to be the same, right? Clearly, something about f tells you something about g, right? There are cases where I tell you something about f, it tells you something about g. Hence, intuitively, those random variables are not independent. Okay? But so there'll be times when it's useful to use the intuitive notion, but usually you should stick with the definition when possible. So let me do an example where they are independent. Okay, let's have the state space omega be Professor Rubenstein takes out a shirt and a pair of pants from his closet. Okay? So let's see. The shirt pant combination will be, let's say this. Let's say it's blue and beige, all right, which is what I happen to have on today. All right. Let's make that with probability. Probability blue beige combination is 0.25. Probability of the red beige combination is 0.25. Probability of the blue green combination is 0.25. Probability of the blue beige, where am I? Yeah, blue beige red green combination. 0.25, right? That's my wardrobe. It would be much harder. We'd have a much larger sample space if we were doing my wife, right? Like we share this big closet. Like I mean, like the length of this board. This is my section right here, right, and the rest of it is hers. Hence, I don't have that many outfits to wear. All right. Anyway, so let's let F equals if the shirt is blue, 0 otherwise, and G is 1 if the pants are beige, 0 otherwise. And let's have a third random variable, H, which is 1 if pants are green. Zero otherwise. Okay? Are any of these pairs of random variables independent from one another? Yeah, which ones are independent? F and G, right. To see that, I mean, really, I have to try this for all numbers. F equals 2, F equals 10, F equals 90. But pretty quickly, you can convince yourself that the probability of that and something else is going to be 0 because F will never be 90. And so and also the probability of, well, let me actually say this. So the probability that F equals 90, G equals 10 is going to be 0, right? Which is going to be clearly the probability that F equals 90 and the probability that G equals 10, right? I mean, any numbers other than 1 and 0 you can quickly rule out in that manner. So we really only have to check with these. Okay, and these are what I pretty much wrote up there. This is all 0.25, 0.25, 0.25, 0.25. So does this match up? So it's gotta equal. Does it equal the probability that f equals 1 times the probability that g equals 1? Okay. Well, probability that f equals 1, the probability that I'm wearing a blue shirt is 0.25 times plus 0.25. Right? This is probability of blue beige plus the probability of blue green, which is 0.5. And this here is the probability of G is 1. That's what? Pants are beige. Blue beige plus the probability of red beige, which is again 0.5. And 0.5 times 0.5 equals 0.25. So this one checks out, right? Do all the others. They'll all check out in the same way. Okay, so yes, F and G are independent. F and H are also independent, right? You'll see for the same reasons. But G and H are not. And to show that, let's just look at the case, the probability that what do I want to do? Yeah, the probability that G equals 1 and H equals 1. Going to be 0, right? Because with the styles this day and age, your pants are generally a single tone, right? Back when I was a kid, there used to be these two-tone pants, one color on the front, one color in the back. This probably before your time. One of those styles that never really caught on. Right there, it would be possible, but you know, with the pants I have in my closet, not possible. Okay. Does this equal the probability that G equals 1 times the probability that H equals 1? No. Again, these are both 0.5. You multiply them together, you get 0.25. They're not independent. I won't be caught wearing beige pants and green pants at the same time. Or whatever. Pull them out of my closet, whatever the thing is. When I take out one pair of pants from my closet, they're either green or beige, they're not both. Okay? That already. Okay, so everybody got independence? Okay, some standard rules, or standard facts, I guess. Rules/facts. Okay, like we already said, the probability of the sum over the probability of all omega over the entire space is going to be 1. Okay, where 0 is less than or equal to p of omega is less than or equal to 1. It's another thing that drives me nuts. Okay, whenever you do a computation for the class, like on your homework, do a sanity check. If you can plug in values for your probabilities and get something less than 0 or greater than 1, you made a mistake. Okay, I mean people are going to do it. I mean this homework that's been assigned. I mean there's some questions where people just put down the wrong answer. And you know, the answer, I'm just like, well, what if p equals 0.3? You have a probability of 7.5. And they're like, oh yeah. You know, I mean, you know, it can't happen. All right. So that's a fact. The probability that x equals little x or y equals little y is the probability that x equals little x plus the probability that y equals little y minus the probability that x equals little x and y equals little y. And this you can see, this is easy to see with one of those Venn diagrams. So here's all of omega. Here's the set of events. This is the set of omega for which x equals little x. This is the set of events for which y equals little y. And in this part, we have the set of events where x equals little x and y equals little y. So if you add up the probabilities of all the events for which x equals little x and all the events for which y equals little y, you've counted this region twice. You've got to subtract it back off. Right? Okay. And the probability that x does not equal x is going to be 1 minus the probability that x does equal x. Right? The probability that something didn't happen is 1 minus the probability that it did happen. Okay, and that goes not just for equality, but the probability that x is less than x is 1 minus the probability that x is greater than or equal to x. The probability that x is greater than or equal to x is obviously 1 minus the probability that x is less than x. You can just, this can be computed from this via algebra. All right. The expected value it's an average. Yeah. Suppose I have a coin. I'm going to toss it. Half the time it comes up heads, half the time it comes up tails. And I'm going to give you $1 if it comes up heads. No money's exchanged if it comes up tails. How much money do you expect to make? Like on the average? Half a dollar. Half the time you'll get $1, half the time you get $0. You do it enough times, on the average you get half a dollar. Suppose I give you $1 if it comes up heads, you give me $1 if it comes up tails. The expected outcome is 0. Because half the time you get $1, half the time you lose $1. In the long run, right, you don't expect to have anything. If we kept doing this over and over again. Okay. So the expected value of a random variable. So let's say x, let's use f. F of omega takes on a small set of values. Let's say it can take on, let's say it's in this set, x1, x2, xk. Okay? Then E of f, which we usually write like that, which is the expected value of f, is going to be the sum over the xi let me just say it's the possible outcomes. Okay, possible values of f of omega of the value times the probability that's the value. Okay? So for our two coin toss examples, the two betting examples. So the first one was win $1 on heads, nothing on tails. Okay? Yeah. So what did we say? Probability of f of h is going to be 1. F of t is going to be 0. The probability of h equals the probability of t equals 0.5. Right? It's a fair coin. Then E of f for this case is 1 for when you get heads, you're going to get $1 times 0.5 plus 0 times 0.5, which equals 0.5. So the expected value of f in this case is 0.5, right? And the second example, win $1 on heads, lose $1 on tails. Same as above. Except f of t is minus 1 instead of 0, right? Because you're losing $1 if it comes up tails. So E of f in this case is going to be 1 times 0.5 plus minus 1 times 0.5, which will be 0. Okay? Okay, now f might take on an infinite range of values. Okay, doesn't matter. So for instance, f could be, the value of f omega could belong to z plus, which is just the set, let's include 0. 1, 2, 3, 4, all the way up. Okay? That's fine. E of f is just going to be the sum from I equals 0 to infinity of I times the probability that f equals I. Okay, again, I'm just using the shorthand notations. Sometimes we drop out the omega when we talk about random variables. Okay, so again, I got some event space. These events happen with some probability. I've got this random variable f. It's a function being applied to that event space. I have some notion of the probability of this random variable f, or this. I'm looking at the set of events for which this function f, when applied to that set of events, equals I. Okay, that's what I mean by probability f equals I. And then I'm computing the expected value of f. I'm summing up over all possible values that my random variable, i.e. my function f, can take when applied to this event space. And I'm basically computing the average value. Okay. Is everyone with me? Okay. I say this already? Yeah. Okay. Now we're gonna be dealing with expected value a lot. Okay. So these are important facts. It won't save your life, but it could save your grade. Okay. Again, another one. When I see people don't remember this, again, it's just, ugh. Because there's like 3 or 4 things you got to remember about probability for this course. This is thing number 1, the most important. Okay. If x and y are random variables, the expected value of the sum of these 2 random variables equals the expected value of x plus the expected value of y. When is this true? Huh? When they're independent? Sure. When else? That's it? Mutually exclusive. All right. No, always, no matter what. It's very, very important. It's an amazing result. Doesn't necessarily make sense intuitively. They could be talking about the same thing, right? I mean, Professor Rubenstein's pants and shirts, Professor Rubenstein's pants. The third coin toss, it's always the case. Proven to be true. Remember that, because there are so many times when this will make solving a problem so much simpler. You break up the problem into the right set of random variables, you're done like that. Otherwise, page after page after page of computation. And there are always some students who remember it. One liner on the exam, they're done. They get full credit on the question. Then there's the other students who don't remember it. They try to work the thing out without using this fact, and it becomes a mess. Never get it right. Yeah, never get it right. I mean, it's just too hard. It's just too hard. It's just an amazingly useful fact. So I don't know. Go home tonight. Tell your friends. Whatever. However you make sure you remember this. Tattoo it on your arm. Remember that fact. That's important. It's always true. So just to make the point, e.g., even if x and y not independent. It's weird but true. And there's another point I wanted to make. Oh yeah, not as important, but again very useful. Is this one. Suppose f is a random variable that only takes values in z plus, which is what we defined before, right? So basically it's 0, 1, 2, 3. Okay? So we have that e of f is going to be the sum from I going to infinity, I times the probability that f equals I. Right? This is by definition. That's definition of expected value. Turns out to be the case, and you can obviously drop the 0, because 0 times probability, you could drop the first term, right? Okay, turns out that this is also equal to the sum from I equals 0 to infinity of the probability that f is greater than I. Okay, note there's no I multiplying here. That's that, and the fact that I'm saying greater is a critical difference. Okay, and again, this is not as important as this other one, but this will save you some time on some computation from time to time. Okay, so why is this the case? It's worth sometimes things are too hard, like the expected value. I mean, this really isn't hard to prove, but I'm not going to do it here. It's like a 5-step proof, especially for discrete random variables. It's true in general for any kind of random variable. This one here, the proof is so easy, and sometimes you don't remember, is it greater than I? Should I start from 1 or 0? It's worth remembering the proof, because the proof is easy. Okay? If I write this out, okay, I can write it out this way. I've got 1 probability that f equals 1, right? And I've got 2 probability that f equals 2, right? 1 times the probability f equals 1 plus 2 times the probability f equals 2 plus 3 times the probability f equals 3 plus 4 times the probability f equals 4 right, etc. Right? So if you look at it going down, you get it in this form. Probability that f equals 1 plus 2 times the probability f equals 2 plus 3 times the probability f equals 3 plus 4 times the probability f equals 4. But if you look at it across, right, this here is the probability that f is greater than 0. F is greater than 0 if f equals 1 or f equals 2 or f equals 3 or f equals 4, da-da-da. This is the probability that f is greater than 1, right? If it equals 2 or 3 or 4 or 5 or 6, 7, 8, 9, 10. This is the probability that f is greater than 2, etc. Hence the bottom solution. Okay? So when students come in my office hours, and I have this we're working out a problem, and e of x plus y comes up on the board, and I ask them, well, what does that equal? When they get stumped, on the outside I'm smiling and being encouraging, but on the inside, I'm imagining like choking them, like, where were you on that, the second day of class? All right. So please don't forget that. Yeah. Only for when the random variable takes on values 0, 1, 2, 3, positive integers. Right. There's also a continuous version that we'll go over. I mean, it can be extended, but the one this one and the continuous the similar one in the continuous sense are the two I want you to remember. Okay, so remember homework 1's been assigned even though it never made it here, did it? Okay, but consider it out. It's available on the web, on the web page I put up before. So download it if you want to get started right away. Otherwise, I'll see you Wednesday, and I'll bring copies on Wednesday. So any questions, send me email. I actually have to run today after class, so I can take quick questions. Otherwise, I got to run. Thanks.